this is an ongoing work. The original one below is something that we are working on with Yuri, and I will be mostly talking about it and the context of it, but practically what we did here and what's new is that we utilized the bright mind of Christoph to solve a very hard mathematical problem. And that was one of the bricks in our big complicated model that we are doing with Yuri. Thank you, Christoph, for that input. That's brilliant. Yeah. So it has started 2018, even before, but okay, it has seen the light in 2018 when Yuri has presented on the Real Option Conference his exercise boundary fitting method. And the idea here is that whenever you are doing with real option valuation, you have some flexibilities to do, and that flexibilities will define your decision trees practically. So the more flexibility you have to choose, the more decisions you will have going out from the decision tree node, and the more complicated it will become. And if you have repeated decisions, then it grows and grows, that tree. Then you have different uncertainties, and it's realistic to have different sources of uncertainty, and then the problem explodes, and whatever method you use in a real option valuation, either analytical or numerical, it becomes very, very hard to solve. So Yuri came up with a very interesting idea of how we can surpass that, and how we can model close to reality complex projects, investment projects, with a lot of flexibility, with a lot of uncertainty, and okay computational demand. Yuri will talk more about that already today, but in that paper he has shown on a very, very simplified example, an abstract example, that the method works, and that is it complies with financial theory of real option valuation, and it actually converges to the analytical solutions if we are talking about very simple problems. Now, what is the model that we are building with Yuri now for more complex investments? We have, of course, some input data and assumptions, yes. Then we have a decision tree block that is practically constructing the decision tree out of all available flexibilities, out of all available choices we can make in our investment. Then it's uncertainties and how we simulate them. And the beauty of the method is also that it's not necessarily GBM or mean reverting process that is generally widely used for these kind of problems. You can do whatever complex modeling of uncertainty you want to inbuild in that process. You can even put you can assign all the values manually how you think everything will develop. So it's absolutely can take anything. And then we also have some optimization criteria, like what we want to get out of that. So all that goes into the cash flow model, where we calculate the value of the all investments actually that can be made within all the decision trees, put against all the uncertainties, and we optimize it with respect to that value. So we want to maximize the overall value on the uncertain plane, and what we get practically the optimal strategies for different development of uncertainty. We will have a closer look at that. But here, what Christoph helped us to do is the decision tree block, and let me show you the decision tree practically. For example, think about modular investment. So we can build one module, we can build two modules, or we can build nothing. And we have, for example, 3 decision times. And that would be the tree. So we can either build 2 at once, we can build 1, and then 1 later, the second decision time, or we can do nothing at the second decision time, and build the second model at the end, or we can skip the decision at the first decision time, build immediately 2 at the second decision time, or just 1 or nothing, and then so it becomes pretty complicated even with this very easy setting. But in reality, what we want to model is that there are, first of all, there are not only that sources of flexibility. There could be some custom-made decisions, custom design flexibilities, but there are also much more decision points in a time horizon of investment, right? If, for example, we are talking about a license for mining, and here we are doing the mining investment, like let's say 20 years, and practically at least 10 years is the reasonable time horizon to keep doing something and to keep making the decisions. So, and if one to reconsider and to think about a new decision at least once a year, so it's 10 decision points already to be realistic. And so this problem in particular, so we need to use that in a cash flow model. So we need to evaluate each path somehow if we build that way against the uncertainties we have. So we need to have some kind of representation of that in a matrix form to match the cash flows, whether there are modules operating or not, when the investment happens, etc. So, but we want to make it flexible in terms of how many time points we have to decide, and then what is the maximum amount of modules we can build. That is what we did. If you look into the proceedings of this workshop, you'll find a brilliant code that allows you, by specifying the number of decision times and the maximum number of modules, to build the matrices that can that represent this tree. And it's tricky. If you like compare the only 2 decision points with 3 decision points tree, it's not clear how to get from one to another unless you're drawing that. So now we have the algorithm behind that, and it simplifies things. So now let's see what the model says when we are running the simulations. A little bit of syntax is in here. So if this is our underlying price uncertainty, then and we run the evaluation, run the simulation and optimization as I described, then we get thresholds for every decision. So what would be the threshold price at the first decision point to build 1 module? What would be the threshold price to build 2 modules? This is actually coming from the exercise boundary, right? But then because we have many decisions, they're getting layers of these exercise boundaries. So, but now these particular values, they are actually not very meaningful, because what is you tweak the inputs a little bit and you get different thresholds, of course. But then what is important is actually how many of those paths from this all uncertainty got into here or into here. For example, 3.41 and 3.51 are very close. Probably, maybe building 1 is just meaningless. So what we want to see is not the price threshold or uncertainty threshold, or how many paths actually has been exercised there. And we'll be further using this gradient to show what strategies are firing in the model, what strategies are optimal. Okay, and here we can see that building everything at once makes sense pretty much 50% of the times. And then building 2 later also fires a bit. But then, for example, staging, building 1 and then another one, doesn't make sense, at least in this setting. Okay, this is how we read this tree. So what we do further, we do a bunch of sensitivity analysis to see how the model reacts to changing the parameters. Now we're comparing investment costs on the x-axis, and also the process, GBM versus mean reverting process. And we can see, of course, that the investment cost has its influence. The higher the investment cost, the more you want to delay because there is uncertain price, and maybe price now is not enough to get your investment profitable. But also, what is important here is the difference between GBM and mean reverting process. And the difference is like substantial. We can see different strategies in here. With mean reverting process that is displayed here, that both processes are fit to the same price, are calibrated to the same price process. So in mean reverting process, we are building here everything at once. In GBM, we tend to delay. So, and I must say, and not just me, it's me about renewable energy, it's Jyrki about mining investments, it's more other reviews in different industries. Mostly real option studies use GBM because it's easier to get analytical solution than with mean reverting process. And a lot of those studies make a conclusion that the more uncertain the environment is, the better it is to delay. It's a classical real option conclusion. So the option to delay is valuable if you have uncertainty. But it's not necessarily the case if the price follows mean reverting process, and a lot of people don't do that. So one should be careful in there, and it's important to choose the process. Our model allows any process to be used. Then we can see what happens if we play with the mean reverting level and volatility. And apparently the volatility on the x-axis, the trees doesn't look very different, but with mean reverting level, the strategy changes. And if the mean reverting level is upward, then building everything at a time makes sense more. Then we are capturing that upward trend with the operation. If it's not the case, then actually some staging appears in that strategy. So many details to understand about what's going on. Then another interesting thing is, what if we play with the speed of extraction? So if we, for example, can extract everything not in 20 years as we did before, but in 5 years, much faster, then actually it makes sense to build not the two modules, but one, and the later the better. Why? Because we can capture the higher prices at the end of the GBM, right? Then, okay, let's summarize. The process is important, the characteristics of the process are important, and the timing of the operations is important. But the model is still pretty straightforward, and we haven't seen staging. Staging would be interesting, and here we are showing that the model doesn't suggest us that it makes sense in an uncertain environment. It's a bit counterintuitive, but it's actually not. When we introduce learning process, here it is, then practically, so if we start operating and mining, then we start to learn how much ore is actually there. If the ore size is uncertain, the mining size, then we come up with very different results. How do we model learning? We model it as some kind of abstract Brownian motion process. Think about learning state, knowledge state, about how much ore is underground. Then we get expert estimates with probabilities of how do they think how much ore is there. And then we use the stopping time problem, so we fit the line to that distribution in a way so on the line crosses these values, these knowledge states, in a way that it fits best the expert estimates. And with this approach, we allow ourselves, we prevent the situation where the mine explores more that is actually there. So this line helps us to prevent that. So now if you operate, you learn. If you don't operate, you don't learn. And so we have two sources of uncertainty now. And this is the price process. At the first decision-making point, the problem is exactly the same as it was before. We only have price uncertainty here. And we have two thresholds to build one module or two modules. And here they're corresponding, the colors in here correspond to the lines in here. So everything that is at this time higher than this threshold builds two modules, and in here only one. And the rest of the green are not built in here. Then at the second decision point, we again have similar situation when we didn't build anything before. So we don't have any better understanding of how much ore is there. It's still the same uncertainty. We have exactly the same formulation. It just happens somewhere here. But then the new interesting part of the decision is here when we build something before and we have been learning something. And now we are making this decision not only based on the price uncertainty, but also based on the uncertainty in ore. And our threshold is not a dot anymore, but it's some kind of function in the surface between prices and between the learning state that we model as uncertain. And so. Well, clearly we get the better our expectation of how much ore is there, and the higher the price, the more likely that we build something in there. So with two sources of uncertainty, we get already a surface, and the boundary becomes not just a dot like this one, but some kind of function. This model still requires a lot of work to do, and particularly now we are working on how to specify to the optimization what are the lines there, or what function do we want to optimize and what would be better, because now it's so far pretty sensitive. Yeah, but when we're done with that, it would be very interesting and already pretty much close to reality model, very complex, and we can extend it to more decision points immediately, and then we can immediately start selling it to industrial guys. And yeah, the important thing in here is that in the model before, where we had only price uncertainty, there was no sense of staging. And here, when we learn, we actually start thinking. In a lot of cases, in 11% of the 100,000 plus, we start staging, building second model after first, because then we get the value of learning in there. Yeah, so we have a lot of things still to work on in this model, and we have a lot of ideas, including that actually which path to stage. Instead of exercise boundary, we will be using a neural net to decide what is better to exercise, which paths are better to exercise. And we are going to expand the model. We are going to make it more realistic, and a lot of work, but a lot of value from that. Thank you.